And it's 2:02, so yeah, let's do it. Okay, so my name is Colin Lennox, CEO, Director, and Ecologist of EcoIslands LLC, and today we're going to be talking about low pH iron oxidation, specifically within acid mine drainage. Now, we've been working in low pH iron oxidation for 2015, 2016 is when we did our first couple studies, and we're doing a new one now in 2018 to continue to adapt our reactors and make some minor modifications, but continue to replicate the work we've done on those first couple years. Okay, I'm gonna close off my actual window here, and let's see if we can go into the background. First time, let's see, still sharing. Hidden webcams are still sharing. People could see you, okay. And let's see, going to go to share screen. Haven't used this one in a little while. Let's see. Let's see, I'm going to present. Okay, now can everybody see the presentation and hear my voice then? It's been a little while since I used GoToWebinar, so just want to make sure. Good, Joe, thank you. All right, cool. Then I don't know if I can get the GoToWebinar out of the way, and there we go, okay. All right, so low pH iron oxidation acid mine drainage using metal removal units. And we've been doing this study now, this most recent one in 2018 since, probably about June is when we actually got the system in. So the newest system's been running for a couple minutes, a couple months. Now there's Dr. Art Rose from Penn State, is Professor Emeritus in Geosciences. He's been doing all the sampling. I've been doing all the maintenance on this new system, this one reactor we have at the new site. And then with the assistance of Pennsylvania DEP, we've got a double-blind study going on for this one. So trying to use the most rigorous possible standards that we can for doing some good science. The 2015 and 16 that you will see then was done, those are single blind. I set up the system. I took the samples myself, and then I took them down to the lab. So single blind, I wasn't doing the sample quantification either. There we go. Okay, so in 2015 and 2016, like I was saying, we set up a system to study metal removal units using organic matrix as a biofilm nest, place for it to grow upon, in acid mine drainage waters that were specifically showing low pH iron oxidation, creating minerals like goethite, jarosite, and schwertmanite, and then seeing, okay, nobody else out in the industry that we could really tell is using anything other than just good old-fashioned two-dimensional surfaces by which to precipitate a minimum amount, but not ineffective. It was effective, but not what you'd call true treatment for the amount of area that you need. And we build bioreactors that are three-dimensional in nature, in that the organic matrix that we use inside the tanks, coconut coir, hemp, there's a whole bunch of different things that we've been using in developing our proprietary recipes, on top of having the reactors themselves be patented as well. And boy, works really well as it turns out. Surface area, wetland surface area, which is it's basically what these units are acting as a proxy for, does an excellent job. So this first picture that you see there, in the first study, 2015 is the one in the background there, and the one in the foreground is two of our Mark 307 MRUs, or a 750-gallon tank. That's 4 by 4 by 8. And that's just as we started off. That was the system had just been turned on in that one day. Yep. Oh, thank you, Earl. Yeah, Earl, by the way, is in Albuquerque. He's one of our newest nonprofit representatives and advocates, and he works primarily in working with golden algae and total suspended solids, and a lot of ponds and lakes in the southwestern United States, a lot of desert conditions, lots of salinity are some of the issues, lots of hard water, lots of evaporation, are many of the issues and instances that Earl's working with, and that's how he found us, and we've been teaming up now for the last year or so in order to find better solutions. Okay, so 2015. Now I live in Altoona, Pennsylvania, and up above Altoona, Pennsylvania is what's called the Horseshoe Curve. Some of you might be familiar with it. And the Horseshoe Curve, it has a lot of legacy mine sites. One of those is Squatter Falls. So 2015, 2016, we had talked to Tobias Nagel with the Altoona Water Authority and asked him, look, man, can we set up this system? We think it's going to work really great. Your water is perfect. We'll go ahead and fund it. I'll take care of all the installation. And in the first year, it worked really well. You'll see that in just a little bit. And then it was worked well enough that they were able to then donate the next year some time and some labor to put in a larger system with 2 true MRUs, or 2 true metal removal units. And you can see over here Squatter Falls 2 and the Squatter Falls pilot. So the pilot then is the polytotes that you'll see in just a moment, adapted to be kind of like the poor man's MRU. Not a very high flow rate. And you'll see that flow rate really matters. As it turns out, higher flow rates are really what you want to be looking for. It's linked to oxygen is one of the things we're finding out. So that's Squatter Falls pilot, and the Squatter Falls 2 was the secondary system. Okay, so the pilot system, like I said, polytotes. 2-inch pipe delivering from a seat that's coming straight out of the ground. Now it was an underground mine adit that was the mine portal, and then the portal collapsed, water's still coming out. And you can see the 2-inch pipe going through the system, and then this is a vertical flow, bottom to the top system. And I had polytotes, and I'm like, all right, let's give this a shot. Like I said, I was pretty darn effective. The average rate, by the way, through there was about 4 gallons per minute. And as time passed, as low pH iron oxidation and Schwarzmannite precipitation occurs, it begins to plaque, kind of like arteries, the pipe. And after just a few months with this system, probably within 2 months, there was a fair amount of ratcheting back in the overall flow rate because it was just getting choked down. By the time we actually finally turned off this system, we probably had maybe a 1/2 inch passage through the entire system. So really it dropped off precipitously, no pun intended. So that is, when dealing with low pH iron oxidation, one of the main points, one of the main reasons why it's never really taken off. Everybody says, my pipes are clogging. But boy, it's not difficult to clean those pipes out, for real. You know, even something is like running a softball down through on a line through is able to knock out everything within the pipe. So it's, you know, saying that they can't do it just means that they're not willing to do the little bit of maintenance work that needs to be done. And that's in the 2-inch system. The larger your pipes go, the longer they last, the easier they are to clean out, because the Schwarzmannite, especially when it's still underwater, is a very soft material. And also goethite and jarosite we found. Were the different mineral forms with it that are precipitating and forming within the system. So we've got a couple different metabolic pathways. So these are biofilm reactors. And in low pH iron water, or waters with low pH that have gotten that way through the oxidation of iron and the production of acid creates what's called basically a selective pressure. You got lots of energy, you've got carbon dioxide in the water already dissolved, and you also have oxygen in the water. And boy, that allows for, just as it turns out, quite a lot of biofilm growth and iron sulfates and different forms of iron oxides, these mineral forms, their precipitation. So we started getting into, all right, so is it more important to look at the individual microbes or the pathways? And ultimately, if you really focus on what the pathways are and providing for the limiting nutrients, whether they be the energy source, the oxygen source, or the carbon source, and then of course there are also nutrients that are involved in this as well. But if you can focus on those big three and really go after those, and decouple a lot of your limiting parameters, then you can get much better rates of treatment. So this is one of the things that really surprised us. That's an iron oxide. That isn't some kind of biological flock. That was material that is gathering and growing, in this case, in the corner of one of, I believe that's the first of the polytotes. And one of the reasons that it's growing in that way is that the material that we're using, a coconut coir, is itself made out of lignin. And it is a very poor source of carbon. And if you're working with chemoautotrophs, or lithoautotrophs, it would probably be a more accurate term because they're using the iron directly, so lithospheric interactions. That when you get a system that, okay, in this instance right here, this picture was taken when the system itself was pretty well full. This is after several months of operation, and I'll show you the data here and the removal rates in just a few moments. But this is around the side of, it's one of the corners. All the rest of the matrix, the organic matrix in the middle of that polytote had filled in and spreads out to the sides. And what you have here, and you can see the wall right next to it, is a form, I believe, of chemotaxis, where biology, now normally you'd think about phototrophism, where a plant leans towards sunlight. Chemotaxis, kind of the same thing, where the additional presence of any one of those primary factors increases the growth. And here in this case, this is around the corner, and you've got more flow, you've got more oxygen, more carbon dioxide, and more iron available. And you get these really neat, almost eyelash kind of growths that are just iron, shortmanite specifically. Now you see here so we're going, this is jumping back. So this is the polytotes. That's 2015, study 1. And then going into 2016, then this is more of the actual coir itself. And this is towards the top. And you can kind of see, I don't know how well, but the material itself, the iron coming out there is grittier. And it forms a plaque over everything, as you can see in that pipe right there. And that's a 4-inch PVC pipe.